to see the magnetic torque of a current loop and then the magnetic torque and the magnetic dipole. So here we have a current loop. This is in 3D dimension, is put like this. If we put it like this, we would have a magnetic field, this that is in this direction, so would be in this direction, and the force that would be exerted on this current loop. It is called current loop because here we have the current going in this or this direction. So we know that the magnetic force is equal to the current times the cross product of the it is length of the wire. Let me call the length. I will put D in this case. Cross product magnetic field, and the length is in the direction of the current. Alright, so we have what would be the force exerted on each one of these parts. So the magnetic field, let's say for this part, so I'm talking about this part. So here the length of the wire is exactly in the, well, is 180 degrees in the direction of the magnetic field. But anyway, they are in the same line, or they are collinear, because magnetic field goes in this direction, like this, and this part of the wire is going in this direction. So here would be no force. Then the same would be for this part, or this part and this part of the current loop. For this part and this part, here we have the current is going in this direction, so all this Y, let's call this part A or D, wherever you want. If it is D, then the force would be the current times D times the magnetic field times the sine of the angle between the length of the wire, this part that is in the direction of the current, so it's in this direction, and the magnetic field that is in this direction. So it is forming a 90-degree angles. So the sine of 90-degree angle is just 1, and so we just have that the force is I times the distance times B. And the same will be for this part. Now just what is the direction of the force? By the right hand rule, we have this distance, or this length is in this direction. We have the magnetic field with the middle finger, and so the direction of the force is going up. So this force exerted in this part of the wire is in this direction, upward. And for this, we have the current is going in this direction, the magnetic field is that way, so like this, and so the force is going downwards. So here we have a force of IdB, and here a force of negative IdB. So actually a force is going here downwards and the force is going here upwards, so we would have a rotation. This current loop would be rotating, so actually there is a torque in this current loop. So what is the torque? The torque is the force cross product with the distance from the center of mass to the point at which we apply the force. That distance is usually called R. Here we have these two forces. Let's say that here is the center of mass, so the torque at this point, let's say point A and point B. At point A, that torque is the force negative I, well, whatever it is, it's just the force at this point. I will put it force times the distance, that is half of L, and the torque of B is this force, force B, here force A, and also we are at half L distance from the center of mass. So the total torque is this sum of these two. Both F's are equal, so we have the total torque is equal to F L, and this is because the cross product is 1. Because we're at 90-degree angles, because this distance is perpendicular to the downward force here and the upward force here. So we just have this force A is, so for the torque A we have negative I dB times R times half L, and for torque B we have positive I dB half L. The direction of this torque is again by the right hand rule. Now the force goes in this direction, the distance is in this direction, so force, distance like that, quite the same with the magnetic field, so like that. Here, distance on the other way, there, and so we have that the torque is in this direction. For this torque, we have force is upward, and the distance for this length is in this direction. So we have that the torque is exactly in the same direction as the previous one, so the torque is going like this. Now the torque will not produce that this current loop will be rotating for the way. This will rotate until we have 90-degree angle. Sometimes if we have a very strong magnetic field, we will have a very strong force, and so they will have inertia, and it could actually pass the 90-degree angle, but then it would return. So the torque is 0 when the current loop is at 90-degree angle. So this is the torque. The torque is the magnetic force, that is I, D, B, and then the length. But the length here times, that is this length, times this, that is the distance, D, is the area of the current loop. So actually we have that the total torque is equal to the current times the area of the current loop times the magnetic field. We would call this quantity the current and the area of the current loop mu. This mu is called the magnetic dipole, and so the total torque is the magnetic dipole times the magnetic field. Look here, this is the area multiplied by the current. If we want to have a magnetic dipole vector, we are taking the vector area vector, that is the magnitude of the vector area is the area of the current loop, and the direction is perpendicular, in this case perpendicular to the loop. So this is our vector magnetic dipole, and so the torque would be the cross product of the magnetic dipole and the magnetic field. This, if you wish, because here we could have put here times the sign of the angle, and so here also the sign of the angle. Now, what is the force, or what is the energy or the work done when we are rotating the current loop from here to a torque of 0? So we will have the integral from theta 1 to theta 2, derivative of the torque, that would be I A B sine theta in dt. So the work done, or energy, is equal to the integral of this sine is negative cosine of theta, evaluated from theta 1 to theta 2, and then all this multiplied by E, I, and A. So here we have and the magnetic field. So this is the magnetic dipole, and so we have that the energy, if you take theta 1 and theta 2 is P over 2 degrees angle, so this would be 0, and so you just have positive theta 1. So you have the magnetic dipole moment, times the magnetic field times the cosine of the angle, and we have two vectors and the cosine of the angle between them. So we have that the energy is equal to the dot product of the magnetic dipole moment and the magnetic field. So whenever we have a body that experiments a torque in a magnetic field, it's called a magnetic dipole, and it has a magnetic dipole moment, that is the current multiplied by the area of that body, and the energy to take that body to 0 torque is the dot product of the magnetic dipole moment and the magnetic field. This is our same current loop, that's this one, just that after the rotation. So we have it like this, put it like this, and now it's in 90-degree angle, so it is like this, and we are seeing it a little bit like this. So now we can see all the forces that are acting here, and these forces would be 0 when it would be exactly at 90-degree angle, but we can sometimes pass a little bit and then we will come back. But it will be 0 at 90-degree angle. And this is like the core of transformers. In the transformers we have current, actually say alternating current, in order of not to be changing for the time and that the generator be doing turns all the time, because if it's only the current in one direction, like in this, then at 90-degree angles it will